This is the weekly review lecture for lesson 8, and based on what I saw, the feedback I got on Piazza, I want to focus on the following three things. So elasticity, logistic growth, and the search function. I mean, concept-wise, there's not much new there. So in terms of pure calculus concepts, it's all about using derivatives, and the new thing in this lesson is essentially applying these pure calculus concepts now into very specific applications, right? Because as you see, for instance, here, logistic growth and the search function is just about a very special type of function that is nonetheless very important in many applications. And same thing with elasticity. In the end, it's about one formula that tries to capture some important aspect about the relation between price and demand. Let's start with elasticity. The basic idea of elasticity is very simple, yet very fundamental, of course, for business applications. Namely, the question is, how does demand react to small changes in price? Right? That is a very important question for you to know if you're trying to sell a certain product. All right, and mathematically, of course, that sets up just the right way for us to use the derivative, right? Because it's small changes in price, right? How do small changes in price affect changes in demand, right? So that is exactly the kind of situation we study using derivatives, right? How do small changes in x affect changes in the function? And now, since we are the producer in this situation, assume to be the producer, what we can control, our x is price. That's what we can control, and the output, so to say, is the demand, right? That reacts to the price. So demand, in this case, we see as a function of price. And here's the basic formula for elasticity, usually denoted by E. It's the percent change in demand divided by the percent change in price. Right? So the most important thing is, of course, here relating somehow change in demand to change in price, right? And dividing this means we get kind of a factor, right? If this, you can immediately see if this is greater 1, then demand will react greatly to a change in price. If it's less than 1, then it means it will not react that much, right? And the reason why you use percent here is because it really you want to get a relative idea, in the sense that, right, if you change the price of some small good by $1, because price is usually measured in dollars. If you change the price by I don't know what, milk by $1, that's a relatively big change, right? Whereas if you change the price of a let's say laptop computer by $1, it's not that big a change relative to the price of the product. That's why we work with percent or relative changes, right? Here. So here's the previous formula in a more mathematical form. The equation of elasticity can be a little bit confusing because of the many fractions that are involved, like a big fraction here, and then in each numerator and denominator another fraction. But let's try to unravel this a little bit. So here we just said Q is demand, right? P is price, and then delta Q is change in demand. And since we're interested in percent-wise or relative change rate, so we just divide it by Q. And same thing for price. We want to see how relative or percent change in price affects percent change in demand, right? So that's why we're doing delta P divided by P. And I marked this here, the main fraction here red, so that you see this is the, we divide this percent change through the percent change in price. Now to derive from this kind of rather monstrous formula, the actual formula for elasticity, we do just a little bit of a algebraic transformation. So let's first write it the following way, right? So we pull out 1 over Q here and 1 over P from here, right? And have delta Q over delta P, right? Here 1 over Q and here 1 over P. Now let's continue right here. This is 1 over Q, right, over 1 over P. We can write this as P over Q, right? Bring the P up, pull the Q down, then multiply by this guy, right? Delta Q over delta P. But now you see, right, this is delta Q over delta P. Q is a function of P, right, as we understand it in this setting, right? Because we changed the price, we want to see what the function demand as a function of price results in that. So this here we can actually understand as a derivative, right? If we let delta P get very small, this becomes the actual derivative dq over dp. So here's the actual function. So here we should have actually thought of, this is more like the approximation. So now E is actually equal to, so if we make this limit here, take the limit that we usually take when we do derivatives, right? We let the changes get infinitely small, right? So we just replace this by P over Q, so the previous one, times dq over dp. And if you think of this now, right here, this term is just simply the derivative of the demand function, interpreted as a function of price. So the one thing you have to do now is, well, if you can remember how we derived this, that's fine. Or you just remember or try to memorize this formula here. Because, oops, I saw I made a mistake here. Of course, this should be a Q down here in the denominator. So let me fix this. Apologize for that. So this should, of course, be Q. So if you want to compute this elasticity, you just need to remember this formula and actually plug in your function. So what you're usually given, and that's also the case in the quiz problems, is a demand equation, right? So you're given an equation of the form Q is equal to something, 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 and the variable in your function is P, right? So what you have to do is then simply compute the derivative, right, in terms of P, plug it in here, and then multiply it by P over Q, where for Q, of course, you have to plug in your equation for P, with containing the variable P again. So I think the best thing is to understand this, how to do it, and it's not difficult. It just requires a few steps that you have to do every time. So let's just go over an example. So here's a problem from the book, a very straightforward problem, but it lets us go through all the steps needed to compute elasticity. So the demand for yams is given by the following demand equation. So always think of Q now as Q of P. So think of Q as Q of P, right? It's a function of P, right? It's given by this function, 5,000 minus 10 P squared, where Q is in pounds of yams and P is the price of a pound of yams. Now, part A is rather easy because it says if the current price of yams is $2 per pound, how many pounds will be sold? Well, that's easy. We just plug in, right? So for part A, we just compute Q of 2, right? Because that's the price, right? So that would be 5,000 minus 10 times 2 squared, so that would be 4, and so that would be 4,960, right? 5,000 minus 40. So now in part B, they ask us for elasticity, right? Is demand elastic or inelastic? We'll come to those terms in a bit, but in order to answer this, of course, we first need to compute elasticity. Okay, so let's do this, and then we see how we go through this formula in detail. So here's our demand equation. Right. Now we need to plug this into our formula for elasticity. Right? Remember, let me also write down the formula here. Is P over Q times dQ over dP. So the first thing we need here is, of course, we need to compute dQ over dP. So let's make this as a subcalculation here. So that would be dQ over dP. But that's an easy calculation, right? Because it's a very easy function to find the derivative of. So that would just be minus 20 P. So that's the first thing you do when you compute elasticity. Always compute this, get the demand equation, right, in the right form, that it's a function of P. Find the derivative. And now in the final step, plug everything back in to this. Right? So now we can write E is equal to P over Q. And now Q is, right, what is Q? For Q we plug in this term, right? Because that's what Q is. Q is given as a function of P. So let's plug it back, plug it in here. So that would be 5,000 minus 10p squared. Right? Now you multiply this by dp over dq, which we already computed, is minus 20p. We can simplify this a little bit and write it as minus 20 p squared divided by 5,000 minus 10p squared. So overall, it's not a nice formula, right? So, but it is a formula, and we can just use it to compute elasticity now at specific values for P, right? Because if we recall, in the problem, we're asked to compute elasticity at the price of $2. So what we have to do now for our problem, we just have to evaluate this at P equals 2. Right? And you see, for instance, here we've already done this in the denominator because it's just Q in the denominator now, right? Because here's the derivative which we pulled together with this term here to get the numerator. So here we already know that's 4,960. Right? Now we just need to plug in P up here. So let's do this on a new slide. So we want to compute E at P equals 2. This was the formula we got for E. Now we just plug in P equals 2, and we would get minus 20 times 4. Right, so here, minus 20 times 4 divided by, we already did this, 4,960. And since we're taking absolute values, right, the minus 20 here actually becomes a plus 20 because it's absolute value. So what we have to do is, right, we have to compute 80 over 4,960. And if you plug this into a calculator, you get that this is approximately 0.016. So now we have a number, and we'll come to the interpretation of that number in a second. But I hope you got from this example how you compute elasticity. So it's essentially just taking this formula, getting the function, the demand function, right? Q as a function of P, price, compute the derivative, plug the derivative into the formula, evaluate everything, and simplify. Then you get a formula of this form that's just expressed in terms of P. And then if you want to then evaluate elasticity, that's what you usually ask in problems, right? You want to know, we're currently selling at a certain price, let's say $2 pound, right? How would demand react to small changes in price here? Well, that's the number that you then get by plugging in P into this equation, right? And you get this number. Okay, now the question is, how do we interpret this number? This is just a number, but what does it actually mean? And for the interpretation, let's recall how we set out to define elasticity. Right? It was measuring change in demand, or percent change in demand, relative change in demand, compared to relative change in price. Now, relative change in price is in the denominator, right? Change in demand is in the numerator. So this will be, if those two are equal, right? So then this would give a value of 1. If this is less than the change in price, right? Change in demand is less than change in price, this would be less than 1. Right? If this is greater than 1, right, that would mean that change in demand is greater than change in price. Now here we have a value of 0.016, so a very small value. In particular, this value is less than 1. That means, right, that going back to our original definition of elasticity, means that a small change, relative change in price, relatively small change in price, will not result in a big change in demand, right? Because this value is smaller than this value, right? Because here we have a number that is much smaller than 1. In this case, we say that demand is inelastic, right? So here are the basic notions. So if E is less than 1, demand is called inelastic because it does not react greatly to changes in price. If it's greater than 1, it does react greatly to changes in price. So in particular, if you raise the price, then demand will go down at a larger percentage, right? And if it's equal 1, then it's called unitary. These are the basic qualitative interpretations of elasticity, right? Because it just tells you unitary, inelastic, elastic. But that's a good starting point, right? To remember, right? So less than 1, inelastic, demand changes little compared to changes in price. Greater than 1, elastic, demands reacts quite a bit to changes in price, right? But since we actually have not only this qualitative information, but we actually have a number, so a quantitative information, we can make this much more precise, this reaction. And on the quiz you find a problem of this kind where you just have to precisely compute how demand reacts to a change in price, right? Given a certain elasticity. So let's ask for example, how does demand react to a 10% price increase? Well, first of all, we would expect that demand goes down, right? If we increase price, we are expected to sell less products, but and that's also reflected in the demand equation in our case, right? It's decreasing function of price. But how much exactly does it decrease? Well, we can use our formula for elasticity and our value for elasticity to do this. So remember, from the original definition, right? E was percent change, percent delta Q divided by percent delta P. So I write this now in a kind of a sloppy but hopefully intuitive way, right? So we are given now, we've computed elasticity. So that was, we know that was it 0.016, and this is now equal to, right, percent delta Q divided by percent delta P. But percent delta P, we know, right? We know that there's a 10% price increase, right? So we can just simply write here 0.1. That's 10%. And this is what we want to know, right? This is what we want to know. Right? This is our unknown. But we can compute this simply now by bringing all the other terms here to the other side, and we get a number there we can compute, right? And you see, if we bring this to the other side, we just multiply both sides by 0.1. So we would get then that percent change in Q, so percent delta Q is 0.016 times 0.1, which is, let's say, about 0.0016. So this is a very small number, right? So in particular, if you want to read it as a percentage, right? So it's a 0.1% change in decrease in demand. So to write it again here, a 10% increase in price leads only to a 0.1% decrease in demand. There you see, this is the inelasticity of the demand in this case, right? So you could increase the price quite a bit, relatively, and don't feel much of an effect in decreasing demand. Correspondingly, if you decrease price by 10%, you don't get much out of it in terms of revenue because you don't increase demand accordingly, right? So if you decrease price, you would increase demand, but the decrease in price does not cause a big increase in demand, right? So that's why if prices are inelastic, you can raise revenue by increasing prices. If they're elastic, right, then just the opposite is true. But the important thing is, here in this example, I hope you see how you can use this number to quantitatively express reactions in demand to changes in price, right? Namely, just plugging in the numbers right? You know elasticity, and you know how much you want to change the price percentage-wise. You just bring this over. So remember what we did here was E, right? So our 0.016, and that was something, that's what we wanted to know, change in demand, and divided by 0.1. So here, this right? You want to know how much you want to change the price. You know the elasticity from the formula before, so you can then compute the percentage change in demand. Depending on whether you're increasing or decreasing price, it will be in decreasing or increasing respectively. So we still have to answer part B fully, and we are now in a position to do this. So is the demand at $2 elastic or inelastic? We saw it's inelastic. And now the question is, how do we interpret this now? Is it more accurate to say people want yams and will buy them no matter what the price? Or yams are a luxury item and people will stop buying them if the price gets too high? Right. So which of the two is it? Think about it for a moment. But the answer should be clear now after what we've, for instance, calculated here. Namely, we see that we could even increase prices by 10% and see very little decrease in demand. Right? So that means people want yams and will buy them no matter what the price. Right? Okay. So let's sum up our observations about elasticity. The first thing is how we derived the formula. This is the formula, and I hope now you can compute elasticity easily. So always remember, find your demand equation, interpret it as a function of P, compute the derivative as a function of P, plug it in here, right? And here we have P and Q again as a function of P. Then you can compute elasticity at any price level. Elasticity as a specific number is always the elasticity of a specific price, okay, or at a specific price. And then we interpreted the value. There's the quantitative kind of coarse interpretation. Less than 1, demand is inelastic. Greater than 1, it's elastic. Equal to 1, it's unitary. Qualitatively, right, there we can even say, using this number that we computed, how large is the exact change in demand given a precise specific change in price. So next I would like to talk about logistic growth. So this is calculus applied to a specific kind of growth function that are very frequent in many settings, so that are encountered very frequently in applications. So the idea of a logistic growth is that while many growth processes are initially exponential, right? So it would look something like that. At some point, there are outside factors which kind of inhibit growth beyond a certain level, right? So, for instance, a population can never grow beyond a certain level because on an island, let's say a population on an island, because there's just not enough space for everyone, there's not enough resources for everyone, and so on, right? Or, for instance, you want to see how many people have cable, or what percentage of the population, right? Since the population is finite, you can't expect this to grow forever, so there will be a limit, right, to where the growth can go, because at most 100% of the population can have it. So you would expect in these cases that the growth function kind of reaches somehow the limit or approaches the limit. And this form, right, that I indicated here in my function that I drew is kind of one way that you could implement such an inhibited or bounded growth, right? And it's not necessarily given that the function should have a form like this, but it turns out that in many processes in nature, this kind of growth, right, inhibited growth, can actually be modeled by a function of this form. First exponential, and then it kind of turns around and becomes kind of inverse exponential. It's still growing, but at a much slower and slower rate as time goes on. And this kind of function, it turns out, can be modeled by a certain type of function called the logistic function. So here is the logistic function. And in fact, there is not just one logistic function, there's a whole family of them, right? Because the logistic function has 3 parameters. So let me rewrite this with color to make this more visible. Here I used colors to the color red to indicate parameters. So L, C, and K are parameters. So you can choose them, but once they are fixed, they are regarded fixed for this specific function P, right? And it is then a function of T. So I indicated T here as blue because T is the variable, and usually it denotes time, right? So once you have a freedom to pick L, C, and K, and the function will look a little bit differently depending on how you choose L, C, and K. But once you've picked them, they are fixed and treated like a fixed number, like a fixed constant, right? That's especially important when we compute derivatives, because these are just constants, right? And T is the variable for the function. Okay, so that looks like a little bit more complicated function. But what I want to do now, and the book gives you plenty of kind of examples where these functions, that describes logistic growth processes and so on, where they occur, but it skips a little bit the mathematical details on the analysis of these logistic functions. So what I thought we do is just look at this kind of function from a calculus point of view and just analyze it from that perspective and see what we can get out of it. Okay. So let's first ask us what happens at time t equals 0. Right? So that would be P0. So here we just plug in 0 for t, and we get that's L over 1 plus C times e to the minus k times 0. So that's 0, e to the 0 is 1. So we're left with L over 1 plus C. There's one quiz problem where you asked to just determine this value P0. And that's actually very easy. You can almost read it off from the function, right? Because you only need the parameters L and C, and then add 1 to C and divide them. And that determinant gives you the value at t equals 0. So observe here that L and C together influence the initial value, so the value at t equals 0. The next thing we want to find out about the function, how does it behave in the long run, right? So what happens for t equals infinity, or going to infinity? Well, Well, let's take a look at the function. Right? So let's write it out here again. L over 1 plus c times e to the minus kt. So what happens to each of these things, each of these terms in this formula, as t gets larger and larger? Right? Of course, there's only one part of this formula where t really plays a role here, right? Namely this one. The rest is just unaffected by it. Right? So what happens? Well, what happens to e to the minus kt if t goes to infinity? Right? If you recall, right, e to the t, if it was just e to the t, it would as t goes to infinity, this would go to infinity. But now we have e to the minus kt. And I should add here, and that's important, that all the constants or parameters are positive numbers. Right? They're all positive. So k is just a positive constant. Right? So think about it for now, it's just equal to 1. Right? So if this is equal to 1, it's just e to the minus t. If it's not equal to 1 but positive, it doesn't change the idea. Right? So e to the minus t, as t goes larger and larger, this will get smaller and smaller. Right? So in fact, this will go to 0 as t goes to infinity. So, but then c times something that goes to 0 still goes to 0. So this whole thing goes to 0. The other two parts here, L and 1, are unaffected by it. So the one thing that we're left with is L over 1, which is just L. So now you can imagine why the letter L is chosen here, because it gives you the limit of the growth process. Right? So it's the how far the growth process can go, how far it can reach, and it will get closer and closer to L as t gets larger and larger. Notice also that the limit value L is larger than the starting value, right? Because we divide L by something that is greater than 1, because c is assumed to be greater than 0. So this is less than L. So we actually have some growth process. We start with this value, and we get closer and closer to L as t gets larger and larger. So what we know so far from just by looking at the definition of the logistic function is that it starts out at L over 1 plus c at t equals 0. Right? And then as t gets larger and larger, it will get very close to, get closer and closer to the value L. Now, what the function does in between, we don't know yet, but we would like to find out. And we can use our knowledge that we have accumulated about derivatives and increasing, decreasing inflection points just to analyze it this way. So the first thing we would like to know about the function, logistic function, is that it's actually a growth function. That means it models a process that's always growing. So we would like to know, is the function that we have in here, is it increasing? Right? It's kind of hard to read this off directly from the function. Right? You could do it, but we have methods for this now using calculus. Right? Increasing. In order to determine this, we just need to compute the first derivative. So let's just do that. So here's our function. Now, what is the derivative? Well, let's compute it. Keep in mind through the whole process that k, c, and L are constant, and t is the variable. So let us rewrite this a little bit so we can apply our rules much more easily. So let's rewrite this as L times 1 plus c e minus kt to the minus 1. Okay. And now we can apply the chain rule, right? So constant multiple just stays, so we would have L times, now we have minus 1, right, by the power rule, 1 plus C e minus kt. And we would have minus 2. And now we have to take the derivative of the inner function here, right? And that's now essentially 1 plus this. 1 is a constant, goes away. So we'd be left with this one. So that would be c times e to the minus kt, because it's an exponential function. And then we just have to multiply the whole thing with minus k. Okay. You should follow along because this is a good exercise. This is a more complicated function with a lot of constants, and it's made out of several functions, so you have to apply rules several times and so on, right? So let's simplify this a little bit, and we get LC minus 1 times minus k is k, LCk times 1 plus CE minus k t minus 2 times e to the minus kt. Okay. Recall that we were interested in finding out if our function, this function here, is indeed a growth function in the sense that it's always increasing. Well, it's always increasing, we know, if the derivative is positive everywhere. So let's check this. Here we have just constants. L, K, and C are constants. They're all positive, so the whole thing is positive. Here we have an exponential function. No matter whether there's a minus in the exponent or not, e to the something is always positive. So this is positive. Now we have this here. Same thing here. This is positive. C is positive. 1 is positive, so this whole thing here is positive. And if we take it 1 over this whole expression square, it's still positive. So we have positive times positive times positive. That's always positive, the whole thing. So indeed, P is a growth function. It is increasing everywhere. P increasing everywhere. So we now know that the function stays in this corridor between L over 1 plus C and L, right? And it's strictly increasing in between this corridor. So now the question is, how does it look like, behave inside this corridor? So it could go to L something like this. It could go like this or something, right? So the question is, what form does it take in there? And the idea, right, that we had that led to the consideration of logistic functions that I tried to indicate a little bit at the beginning is that many processes start out as exponential processes, and then kind of turn around. So they start out something like this and then kind of flatten, right? And if that's the case, right, so they start out as exponential, that would mean that there's an interval where the function is actually concave up, right? And then it turns into concave down and remains that way as t goes to infinity. If that's true, then there must be an inflection point somewhere here. That means the second derivative must have exactly 1, 0 here. So bear with me now. We're going to compute the actual second derivative. It's great exercise. It's not easy, but try to do it yourself and see if you get the same result that I get. Okay, so we want to compute the second derivative and see where it has a 0, so we can see that there's actually a inflection point there. So I've copied the first derivative that we've already computed over to this slide. I switched these terms. It just looks nicer to me this way, but that's a personal preference. So we want to compute the second derivative now. And now you see the function is even more complicated. So let's start doing it step by step. LCK is just a constant, right? Product of constants that just we carry with us. Now it's a product of two functions, right? So I suggest we use the product rule. I like the product rule personally better than the quotient rule. You could also apply the quotient rule because you could write this as ek minus kt over 1 plus c e minus kt squared, right? But that's personal preference again. I always forget, because there's an asymmetry in the quotient rule, where is the which part goes on which side of the minus, whereas the product rule is symmetric, right? So you can't go wrong there. So I'll use the product rule here. So let's take the derivative of this one here, multiply it with this. So that would be e to the minus kt times minus k. That's the derivative. And then we multiply it by the remaining function, 1 plus ce minus kt minus 2. I might have to use multiple lines here because it's the function is getting too long. So let me start a parenthesis here. So then plus, and now we have to keep the first expression, e to the minus kt, right? And now take the derivative of the second function, right? So that is again now an application of the chain rule. So that would be minus 2 times 1 plus ce minus kt minus 3. Now we have to multiply this by the derivative of the inner function, 1 plus ce minus kt. We've already computed this before, right, when we took the first derivative. So let me just add this here. So this would be c times e to the minus kt times minus k. So it's a long expression here. So let's try to bring a little bit of order into this mess here. So LCK we always have. Now we see we have several e minus kt's here, right? So let's bring one of them out. So we can bring this out, and then we have e minus kt here. There's another one, but let's just bring one out now. So we'd have e to the minus kt. And we also see we have a minus k here and a minus k over here. So we can also bring that on now. So we have minus k, right? And then we see we have a minus 1 plus c to the e minus kt minus 2. Here we have the same term but minus 3, but we can bring the minus 2 one out. So we'd have 1 plus ce minus kt minus 2. And now we'd be left with, so times, here we see we actually brought everything out from the first term here, so we just have 1. plus, and now let's see, we brought the e minus kt out, so we're left with minus 2. We're left with one instance of this parenthesis here, so 1 plus c times e to the minus kt to the minus 1, right? And we're left with another c here, right? The c times c time and an e minus kt. So I think this is as far as we can take it. We can of course revert this as minus 2 times blah 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 blah. But let's leave it this way. Now let's recall what we actually set out to do. We wanted to find if this function has an inflection point, and if so, where. Okay. So we have computed the second derivative. Inflection points are given by the zeros of the second derivatives. Right? If they're there, then the second derivative must be 0. So let's see, where does this expression have become 0? And now it's really important again, recall L, C, and K are constants. We have no influence over them, and they are positive. The only thing we have influence over is t. So this is positive. E to the minus kt is always positive. Minus k is just a constant. 1 plus this stuff here is positive to the minus 2 stays positive. So this part here of this product, right? So it's this times this parenthesis here, square bracket stuff. This part will never become 0. So the only thing that can possibly become 0 is that term, that expression that is here enclosed in the square brackets. So let's look at this a little bit more closely. I'll copy it over to the next slide. So I've copied this expression over, and I've already set it to 0 because that's what we want to do. So, and we want to solve this for t. That's quite a challenge, but it's a good one. So if you can do it, you never have to worry about your algebra and exponential functions and so on again. So let's do it. Let's first rewrite it. Multiply both sides, I'd say, by this expression, right? So then we would get 1 plus CE minus KT minus 2 CE minus KT equals 0. So we can simplify this here now, and we get that this is 1 plus, oh no, it's minus CE minus KT, and that's equal to 0. So in other words, CE minus KT is equal to 1. Right, and now we can solve now using logarithms. So we would have that E minus KT is equal to 1 over C, and hence minus KT is equal to ln 1 over C. And then finally, this gives us T is equal to minus 1 over K times ln 1 over C. So in fact, we found the 0 of the second derivative, Right? So this is now the zero of the second derivative, and indeed an inflection point occurs there. So once again, our inflection point occurs at this time, t, minus 1 over k times ln 1 over c. So that seems a little okay, we know it, but this time seems a little weird, right? So it doesn't seem to give us much information. But something very interesting happens if we want to find out what exactly is the value, right, of the function at the inflection point. Okay, so what is the value of the function? So let's plug this back into p. So let's compute p of t at this specific t, right? It would be L over 1 plus c times e to the minus k, and now we have to plug all this t back in here, so it would be minus 1 over k times ln 1 over c. Now let's try to unravel this here. So it would be L over 1 plus, what do we get? We get c. Now e to the minus k times minus 1 over k is just 1, right? So this times this is 1. So we'd be left with e to the ln 1 over c. But e to the ln is just whatever comes after ln, and that's 1 over c. So it's c times 1 over c, which is 1. So it's, let me just write this out, times 1 over c. So the whole thing is L over 2. So what this means is that the inflection point, at the inflection point that we computed, the growth reaches exactly half of its capacity, right? Namely, half the limiting value. So here's the picture that we get now, right? We have the initial value, L over 1 plus c. And recall, in the quiz, if you're asked to compute the initial value, you only need to extract from the function that you're given the values for L and C and compute this value. We have the limiting value L, that's also easily extractable from the function, right? There, we've established that it's increasing everywhere, and now we've established that it has an inflection point, right? In the inflection point, the time itself is a little bit complicated, but we've observed, made this interesting observation, that the function flips, right, from concave up to concave down at exactly the point where the value of the function reaches half the limiting capacity. So this fact has numerous interesting applications you can read about in the book concerning kind of sales predictions. It's also called the point of diminishing returns. So what this means, so mathematically, just notice that this is the point also where the function has its steepest growth, right? So where it grows most quickly, right? And then growth slows down from then on. So what we get from this is that while the logistic function is a rather complicated function and the derivatives are quite demanding, as we have seen, right, the basic facts that are often used are not that hard to capture. So I've just listed the 3 basic facts that you will need mostly in the quizzes, namely the initial value, the limit value, and the inflection point. And the inflection point occurs where the function value reaches L over 2. So what that means is, so in the quiz, and I want to give you this hint for the quizzes, in the quizzes you're asked, there's one type of problem, you're given a logistic function, and you're asked at what time is the second derivative 0? And of course, what you could do is now compute the derivative and solve it just as we did. But there's an easier way now to do it. So let me do this on a new slide. So if you are asked at what time is p double prime of t 0, you could either solve this, of course, the hard way by computing the second derivative and solving for solving this equation for t. But you could also say, okay, I'll just need to find the t when p of t becomes L over 2. Right? And L you can read off, right? So L you can read off from the equation, right? From the logistic function. And this is just the logistic function that's given to you anyway. And this becomes, right, in this case, you would just have to set it up like L over 1 plus C of times e to the minus kt equals L over 2. And of course now in your application, L, C, and K would have specific values, right? But it really does not make a big difference. You just plug in these specific values and solve this whole thing for t. For t, right? So that means you just have to solve an exponential equation here, right? And what you will actually get is, of course, then the value for t that we computed before by solving this this equation here, second derivative equals 0. But now that we know it, we can also go through this, right? And it makes things much easier, right? So you solve this for t and you're done. So you don't even have to, because we just demonstrated that, right? That the inflection point occurs exactly at the point where the function reaches half the limiting value, right? You can now use this knowledge and compute the inflection point in turn by just solving this equation here for t. Okay, I hope you find this helpful. So the last topic is the search function. I want to keep this brief, so not to make the video too long. And also there's not really that much to say. People asked me how on Piazza, they asked if I could go over how to compute the derivative of the search function. So I'm not going to say anything about the motivation of the search function. In general, the search function is again a whole family or class of functions with parameters a and b. So we have a and b positive constants, and then we have the search function y equals ate minus bt, where again t is our variable and a and b are constants. And the form of the function looks something like this. It starts out rather steep, has one global maximum, and then declines to 0. Right? Decreases towards 0 as t gets larger and larger. Of course, now the main knowledge you want to have about the search function is where does it reach the maximum, right? And where does, what is the value at the maximum? Well, this is then a straightforward exercise, as we know, because finding maximum, we know it. So supposing or assuming we already know it has exactly one global maximum, all that's left to do for us is to compute the derivative of this function, right? And find the critical points. Okay. But compared with a search function, with a logistic function, this is actually not too bad, because we can just apply the product rule. So y prime would be, and now keep in mind all the time that a and b are just constants. So a we just keep with us, and now we'd have the derivative of the first function, right? So let's say this is the first function, this is the second function. Derivative of the first function would be just 1, so we just have e minus bt, and then plus first function t times derivative of the second function, so that's by the chain rule e to the minus bt, and now we have to multiply this by minus b, because it's the derivative of this inner function here. Okay, so we can simplify this a little bit more, and we get a times, we can pull out the e minus bt here, right? And then we'd have 1 minus bt. So that's the first derivative. Now the question is, what is the critical point, or where does it occur? And for that we have to just simply set this equal to 0. Right? For which t is this equal to 0? Now we can go over this expression again. A is a constant. This will have no influence whatsoever about this product being 0, right? Because it's constant greater than 0. So a we can discard. E to the minus bt, e to the anything is always greater than 0. In particular, it's not equal to 0. So that will also have no influence over this whole expression being 0. So the only thing that could make the whole term 0 is this parenthesis term here in the parenthesis, 1 minus bt. So this is 0 if and only if 1 minus bt is equal to 0. And that's the case when, exactly when t is equal to 1 over b. So here is our critical point. And now you could go on and do the whole thing about finding out whether it's a global maximum, it's a local max or local min, using, for instance, the second derivative test or just the change of sign test. But I'll skip those details now. So the most important thing you have to take away from this is that here at 1 over b, the global maximum occurs for the function. So the two things you should take away again from this. First is the way to calculate the derivative. It's a simple application of the product rule plus a little application of this chain rule here. Here is the value or of the function, the first derivative as a function. We determined the critical points. So in the quizzes, you are asked two things. You have to find the value of the derivative at a certain time. That you can do using the equation or the formula for the first derivative. And then you're asked to find the maximum, let's say, of a concentration of a substance in the bloodstream. For that, you have to simply compute the critical critical point. But that for that you don't even have to compute the derivative, because you can just simply read it off the function, because you just need 1 over b. And then when you have, so you compute 1 over b, when you have that t, you just plug it back into the original search function and compute the actual maximum value. Right? Okay, so there's really not much to it once you understood how this setup works and what to do. So a search function, I think, should not be too bad with this brief summary. Okay, I think we're done for this time. I hope you find the explanations helpful, giving a little bit more background on these three important applications.